Hello, everyone, and welcome you to the first keynote session in ICDCS 2021. Good morning to US friends, good afternoon in Europe, and good evening in Asia. My name is Xiaodong Zhang from the Ohio State University. I'm happy to chair this keynote session. Our keynote speaker today is Professor John Ousterhout. John is the Bosec Learner Professor at Stanford University. He received the 2020 IEEE TC DP Outstanding Technical Contribution Award and the ICDCS High Impact Paper Award. We reserved this keynote with John last year in the ICDCS conference. John is best known for several of his research projects that have made a high impact in both academia and industries. So let me briefly introduce his impact in the log style, because one of his research is log file systems, so in time sequence. In 1970s, he was a key player in the CM-star distributed systems at CMU when he was a PhD student. In 1980s, he developed the concept of co-scheduling and Gantt scheduling, which are commonly used in distributed systems and networking system today. His 1982 ICDCS paper about the concept received a high impact award last year. He created a Sprite operating system with his students at UC Berkeley in 1980s. In 1990s, he developed the log structured file system that has also been used widely in production systems. 20 years ago, he led RAM Cloud project. Since then, in-memory computing has become a common practice in daily computing operations. In 2014, John published the Raft paper with his student Diego. Raft has been quickly adopted in industries. In 2018, he published a book, A Philosophy of Software Design, where he emphasized that the problem decomposition is the critical issue in software design. John received ACM's Software System Award. He's a member of US National Academy of Engineering and a fellow of the ACM. So let's welcome John to share his story of Raft with us. John, it's your turn.
Made the classical mistake, muted myself. Thank you very much. And I'm really delighted to be here to talk to you today. So let me share my screen. Okay, hopefully everybody can see my slides now. What I'd like to do today is to tell you a little bit of the backstory behind the development and eventual adoption of the Raft consensus algorithm. So the stuff that we didn't talk about in the technical papers. And the talk is going to have two parts. And the first part, I'm going to give you a little bit of the history. So how did the Raft algorithm come about? What caused us to develop it? And I want to talk about the difficulties we had in getting it published, and also a bit about its adoption in industry and also heavy use in academia. And then in the second half of the talk, I'm going to step back and talk about some of the takeaways that come to me, I think, from the project. The two biggest ones, I think, are first, the notion of intuition, I think, is really underappreciated in software design. I'm going to talk a little bit about that, and also compare that to a more formalistic approach. And in particular, Leslie Lamport and I have pretty different philosophies. I'd like to compare and contrast those. Another big takeaway is that program committees are really challenged today. I think that they're not very good at identifying impactful work. I want to talk a little bit about that, and also make us a charge to those of you that will be on program committees in the future to, I think, change the way you think about papers when you're reviewing. And then I have a few other philosophical observations to make as well. So let's dive in. The Raft project got started, honestly, because I couldn't understand Paxos. So at the time, we were building RAM Cloud, which was a distributed storage system for data centers. And in the fall of 2011, we decided that we needed to have a consensus-based storage system for managing the configuration information for the RAM Cloud cluster. Diego Ongaro, who was one of the students working on the project and ended up being my co-author on the Raft paper, suggested we should implement Paxos. And that made total sense at the time. And Paxos is really the gold standard for consensus. In fact, the term Paxos and consensus had become synonymous by that time. But I wasn't that familiar with Paxos at the time. So I said, Diego, why don't you explain to me how it works? So Diego spent one of our weekly meetings and explained it to me. And honestly, I didn't get it. So the next week, we met again. I said, Diego, I'm still confused about Paxos. Tell me again. He explained it again. I still didn't get it. Then I had him write the algorithm on my whiteboard. And the funny thing is, it's only about 5 lines. And I left it on my whiteboard. Every day when I came into work, I'd look at that and stare at it and try and figure out how this worked. And boy, I just had a terrible time wrapping my mind around it. How can 5 lines be so difficult to understand? So then I tried various other things. So for example, I tried to read, there's a famous paper called The Part-Time Parliament by Leslie Lamport that explains it. Anyone who's read this paper knows it is an extremely difficult paper to read. Rather than tell you my impressions of it, I'd like to read to you a comment I heard from another senior researcher who said, the paper is terrible. It's beyond terrible. It's a detriment to the entire idea of clear communication. It should be simultaneously shot at dawn and entombed in the mausoleum of unclear scientific writing. And I was not able to understand that paper. I think most people who read it are not able to understand it. So then I read another paper by Leslie Lamport, Paxos Made Simple, which was a little bit more understandable. And it focused on the single decree, simplest part of Paxos. And I started to get some clues about how it worked. And what I found interesting is that this paper had an informal proof of correctness about why Paxos worked, why it was safe. And I was able to understand the proof enough to convince myself that indeed it was correct. And Paxos was in fact safe. And yet I still couldn't understand why it worked. That bothered me, that somehow I could believe that it worked, but I couldn't understand why. I couldn't get any intuition about what was going on to make it work. So about this time, I attended the NSDI conference, which is a big networking conference in February of 2012. And as I went around having hallway conversations with people, I did an informal survey. When I was in a group of people, I'd ask them, so do you all really understand Paxos? And what's interesting is that everybody except one person gave some variant of no. They say, well, a little bit. No, I don't really get it. Well, partially. No one really understood Paxos. And these are networking experts, except one person. Tom Anderson from the University of Washington. Yeah, of course. Yeah, it's easy. In fact, it's so easy. We teach it to all of our undergrads and they implement it. Well, this was surprising to me and seemed to conflict with what I was hearing from the other experts. But it turned out that we had an incoming graduate student at Stanford who was from the University of Washington, Amit Levy. And so when I got back to Stanford, I looked up Amit and I said, is this true that undergrads implement Paxos? He said, oh yeah, he said, I implemented it, but honestly, I haven't a clue how it works. And so the story was consistent here. And this struck me as really bizarre because consensus is probably the single most important algorithm in all of distributed systems. And if it's this important, how can it be that as a community, we can't understand it? The thing that is the most important algorithm. So this just seemed fundamentally wrong to me. So why is this? Well, over time, I think I've gradually figured out what are the problems with Paxos. It's really hard to develop intuitions about the basic Paxos algorithm. To me, I think of it as it's like a tiny little knot where you can't follow the thread as it goes through the knot. There are 2 phases in Paxos. Each one is dependent on the other phase. And there isn't really a clear intuitive explanation of what each phase does. Together, they do produce a safe implementation of consensus, but it's hard to say what is the first phase and what is the second phase. In fact, the names are even kind of confusing. And you can't wrap your mind around, well, why do these work together to produce consensus? So the basic Paxos algorithm is very concise. Again, only 5 lines, but it's not simple in some way. A second problem is that this basic Paxos algorithm, the single decree Paxos, is way incomplete. It only agrees on a single value, and in practice, you typically want a series of values, such as a log. Second, Leslie only addressed the safety issue, not liveness. And we know in distributed systems, there are two important properties. There's safety, which says that the system does not do anything wrong. And then liveness, which says it actually makes progress and does things that are useful. Well, liveness was not addressed at all in the Paxos discussion. And it's really important. In fact, in practice, liveness is as hard to achieve as safety. It's not as interesting, but it's hard to achieve. And in addition, the Paxos description didn't describe things like, well, how do you choose proposal values and how do you manage cluster memberships? There were all these things missing. And then finally, as described in the Paxos papers, it's inefficient. It takes 2 rounds of messages to agree on each value. And in practice, you can do this in 1 round, but it takes a slight reorganization of the algorithm. So there are all these additional things you have to do to make Paxos really useful, but there is no agreement in the community on how to do that. Everybody does it a different way. There are no papers written that are sort of provide standards for that. So if you're thinking about implementing Paxos, what you have to do is you have to extend what's written in the literature by a lot, like a factor of 3 or 4x in terms of overall complexity. And you have to make fundamental modifications to the algorithm to make it more efficient. But you have no intuitive basis for doing that because you can't understand. It's really hard to get intuitions about the algorithm. And that's just a really bad combination. So this problem kind of ate away at me for a while. And I felt like as a community, we need to do better than this. Surely we can do better than this. So what I decided to do was an experiment. By the way, meantime, Diego was off implementing Paxos. But I decided to try an experiment. What if I just start from scratch and design a new consensus algorithm? What will happen with that? And one thought I wondered is, well, does this turn into Paxos? It must. Is it just fundamental that the Paxos algorithm is the only one that works? And so I'm going to end up there sooner or later. That would be interesting to see. Or in any case, by working on it from scratch, I thought I'd get a better appreciation for what the problems are, and it would help me to understand Paxos better, and maybe I'd be able to develop intuitions that I hadn't been able to develop so far. So I started working on this, and I gave it the name Alpo, which I believe is probably one of the worst names ever chosen for any research project or systems in the history of computer science. But Alpo stood for Alpo is like Paxos, except more obvious. And you may know Alpo is actually the name of a dog food. And so I thought if we developed Alpo and it actually turned into something we use in RamCloud, we'd be eating our own dog food, which is a popular expression around Silicon Valley. Anyhow, truly dreadful name. Fortunately, Diego had the common sense to come up with a much better name for the eventual Raft algorithm. So I worked on this for a while, and in fact, it wasn't turning into Paxos. It was a different formulation, and it felt to me like it was really more obvious than Paxos. So at this point, I challenged Diego to a bake-off. The idea is that first I would explain Alpo to the RamCloud group, and then he would explain Paxos, which he was implementing, and we'd ask the group if one of those seemed more obvious or easier to understand than the other. Now, this was probably an unfair competition because I had a lot more experience than Diego at explaining things, so maybe this wasn't really fair. But we did this, and the group agreed. It seemed like Alpo was a lot simpler and easier to understand than Paxos. So at that point in time, Diego decided he would implement both Alpo and Paxos, and then we could compare those and see how those turned out. So at that point, Diego and I started working together to refine the design of Alpo. It was still pretty incomplete and buggy at that point. By the way, if you're curious, there's an Alpo design document that's available on the web in the RamCloud wiki. It's still there. You can look back. It has actually a lot of the features of Raft, but it's different in some fairly significant ways. So Diego and I started working on this, and we decided our primary goal was going to be understandability. That's what we're trying to maximize in this new consensus algorithm. Well, that's an unusual metric. People often design for correctness or performance. I don't know of many systems where that's been a primary goal. And of course, the system had to be correct as well, and it had to be reasonably performant. But really, our fundamental goal was to see if we can make the system as understandable as possible. Now, you might ask, is that really important? Why does understandability even matter can't you just have an implementation that everybody uses, and so people just use it, nobody needs to understand it? And furthermore, can't the people implementing it just follow a spec that's already been done? So maybe only one person or group, the original designer, really needs to understand that. Everybody else can just work off of this. I don't think so. I don't agree with that. I think intuition is really important in building software systems, because sooner or later, any implementation is going to deviate in some ways from the spec. There's no way to perfectly implement the spec. And intuitions are what allow developers to make those extensions or modifications and do them in a way that is safe and that works. They'll allow them to do that without introducing bugs. I think intuition or understandability is really important. Well, then the next question is, well, how do you make a system understandable? If we want it to be more, what do we do? And we thought about this early on in the project. We decided, we tried to identify, so hypothesize some approaches that we thought would make it more understandable. And there were two that came out in particular. The first one, of course, is the classic modular design problem decomposition. It's at the heart of all of computer science. And so we tried to decompose the consensus problem into a set of smaller things that could be understood relatively simply, and each one of which would have a clear intuition. And in particular, the final Raft algorithm ended up with 5 basic properties, each one of which has a very clear intuition, and they build on each other linearly so that the final of the 5 properties is in fact the Raft safety property. Now, the second way of improving understandability was by trying to minimize the state space, reducing special cases, trying just to minimize the complexity of the design. And the way to do that is that you have to find single mechanisms that solve many problems. If every distinct problem requires a separate mechanism, then you're going to have a lot of complexity, a lot of state space. So we tried to figure out, what can we do? What are the components we can use to build Raft that have the highest generality, that would give us the most bang for the buck, most functionality for the least complexity? Well, this was a really fun process. Honestly, one of the most fun design process I've ever had in my career. So the way that we would do this is that between us, Diego and I would try and come up with a couple of alternative designs for each of the major issues. And then we would try explaining them to each other. And the question was, which approach is easier for us to explain? And so we try one, and that would seem really complicated. So we try another one, and we'd iterate over this until we eventually found solutions that to us seemed really easy to explain to each other. Meantime, Diego was actually implementing all of these in a prototype implementation. And so that helped also to ensure that what we were thinking about was actually practical and would work in progress, in practice. Sorry. This was really fun. Really, Diego and I both had a blast doing this. So as one example, leader election. In order to do consensus, you have to make sure that only one server is replicating information at a given time. And the main problem is, what do you do if several servers try and become leader at the same time? In my original Alpo approach, I used something similar to what Paxos used, where each server is assigned a rank, for example, based on a server ID. And the idea is that the highest rank wins when there's a conflict. Well, it turned out this led to a whole bunch of corner cases and a very complex state space, most of them related to liveness. Now, the reason this wasn't a problem in Paxos is, again, they didn't deal with liveness, and so they didn't encounter all of these problems. But things like, what if servers arrive in different orders, or what if the highest ranked server crashes partway through the election process? How do you roll over to the next lower server, and so on? And so as we were trying to refine this, the explanations just got more and more and more complicated. And so then at some point in our discussions, this notion of just using randomized timeouts appeared. Just collect votes from each candidate that wants to become leader tries to collect votes from other servers. Each server only gives one vote. If you get a majority, you win. If you don't get a majority within a certain time period, then you just reset, start a new election, and start again. It turned out this was a really simple mechanism. It eliminated the need for any sort of ranking mechanism. And it turns out you have to have timeouts for liveness. One of the fundamental properties of distributed systems is if you want to be live, you have to have some sort of a timeout mechanism to detect crashes. And so it turned out that the timeout mechanism solved multiple problems. It handled both the crash problems, it handled split votes where multiple servers try and become leader and nobody can get enough votes. It handled all of those in a really clean, really simple way. And it was just obvious that this was correct. It had all the nice properties. So that was an example of trying to find a mechanism that was easy to explain, led us to a really simple approach. Okay, so we worked on Raft. We got to the point where we were pretty happy with it. And then we decided to publish it. And we debated whether this would be publishable. Does the world want to hear about another consensus algorithm? And so I argued we should try and publish this, but I told Diego at the beginning, this is probably not going to be easy. This is going to generate a lot of hate for a bunch of reasons. First, we're goring a sacred cow. Paxos was the gold standard at the time. And program committees are going to be defensive about that. They're going to try and protect that. Second, we're using this very strange metric, understandability. PCs, program committees are not going to be familiar with that. They're conservative. They don't like things they don't understand. They're probably going to reject that idea. And third, honestly, how do we prove that Raft really is simpler? We think it is. We initially debated doing a user study and thought probably didn't think it would be convincing. And so we realized that there were problems. And indeed, program committees just rejected it over and over and over. It was rejected 3 times before finally being accepted to Usenix in the summer conference of 2014. So what happened with the reviews? Well, so I've got a bunch of extracts of reviews over the various submissions. And first of all, the issue of understandability was in fact quite controversial. There were some program committee members who actually believed us. They said, yeah, Paxos is hard to understand, and yeah, Raft is easier to understand. Those are some comments for those who are on the left side of the slide. I'll just read a couple of my favorites. One of them says, the dirty little secret of the NSDI community is that at most 5 people really truly understand every part of Paxos. Or another one, Paxos is a consensus protocol that is easy to understand in its full complexity if your name is Leslie Lamport. Mere mortals have been less successful. So there were some people that bought our arguments, but there were others that didn't. For example, some reviewers didn't think Paxos was all that complicated, or others didn't think that Raft was obviously simpler than Paxos. And then others, actually the one I found most disappointing was reviewers that didn't even think that simplicity really matters. I'm not convinced that simplification really makes sense. That to me was, I felt was sad because I've always been really a lover of simplicity. I feel like it's one of the most important things in designing software. So this was controversial. But if you looked at the reviews, the paper actually got high reviews. So I've included the summary of the reviews from the 3 conferences, 2 of the rejected conferences and from Usenix. What's interesting is that these reviews are actually consistent with accepted papers. I have never received a paper that gets reviews this good and ended up being rejected over my career. For example, in NSDI 2013, there was only 1 review that was less than a borderline accept. Same thing with NSDI 2014, and yet the paper was rejected. So what was going on? Well, I wasn't in the program committee meeting, so I don't know for sure, but I have a hypothesis. If you look at the most negative ratings for the papers, and then you look, each reviewer typically gives their confidence in their review, which is typically an expression of how expert they are in the subject area. Well, it turns out the most negative reviews came from people who were experts in the area. And my experience in program committees is that when there's any doubt about a paper, you tend to defer to the experts in the area. So what was happening is the experts, well, they were familiar with Paxos, probably didn't see it as being complicated anymore, didn't see the need for anything new. And so they were causing the paper to be rejected because the PCs were deferring to them. But in fact, our audience, actually the audience for the paper was not the Paxos experts. The paper was actually intended for all of the other people who in fact found Paxos pretty confusing. So it's interesting to see what happened with the reviews. But there were problems with the first version of the paper. And that's, of course, that's always true. Every time I submit a paper, we always learn a lot from the first round of reviews. And in particular, we hadn't attempted to actually evaluate understandability, and we didn't have a correctness proof. And the program committee objected to both of those things, and those were valid objections. I agree with that. So we decided to try and fix those. So Diego worked on a correctness proof, and then together we decided, let's just bite the bullet and see if we can do a user study to try and evaluate understandability. So I'd like to talk a little bit about the user study, because that was actually very interesting to me. First, lesson from this: user studies are really hard, huge amount of work, and you don't have any idea whether it's going to work until you get to the very end. So this process really increased my respect for the people in HCI who do user studies all the time. But the big question is, how do you measure understandability? And so what we decided to do was to teach a collection of graduate students about both of the systems. And we teach some students in one order and other students in a different order, and then try and test their understanding and see, can we measure whether the students in general understand one of the systems better than the other? We were fortunate that at the time there were graduate classes in distributed systems underway at both Stanford and Berkeley. And the instructors for those classes agreed that we could use their students as subjects. This was a huge help. But that still left us with a difficult question. So how do we do this in a way that's really fair and that's meaningful? And in particular, how do we teach and how do we test? We were fortunate that Scott Clemmer, who's one of our faculty at HCI at Stanford at the time, worked with us. He was a tremendous source of help in helping us to design the experiment. So first, how to teach. Well, what we decided is we would do a video lecture for each of the systems. And the reason for this is that way every student sees the same experience. Students at Berkeley, students at Stanford, and students can learn the systems in different orders, so they're watching the videos at different times. And then we would make sure that the videos covered the same functionality for each system, so a replicated log, all the way up to a replicated log. Next question was, well, who teaches the video? And one possibility was that I would teach Raft, and then we get somebody else who's a Paxos expert to teach Paxos. And that was actually our first choice at the time. And that does have the disadvantage that with different instructors, they could have different skills or techniques, and that could potentially influence how well people learn the systems. The other alternative is for me to teach both of the systems. And by the way, by this time, I actually was pretty comfortable with Paxos. I felt like I could teach it effectively, but the confounding factor there is clearly I like Raft better, and would that influence my teaching, so I would do a better job on Raft. So we initially planned to use the first approach, and David Maziere was going to teach the Paxos lecture, but our timetable for this was so tight to get this into the classes and get the results in time for a conference submission that David wasn't able to prepare a video in time, so I ended up doing both of them. One other twist is that, as I mentioned before, there's no generally agreed upon algorithm for log replication in Paxos. So I had to invent one, kind of pulled from pieces of various papers and tried to find the simplest possible approach for that. So I did both of the videos. And by the way, these videos are both available on YouTube still. If you just Google, I think if you Google John Ousterhout Raft lecture, I believe, it'll on YouTube, it'll take you to both those videos. You can see them. Second issue is, how do you test? Well, and the main problem is, how do we do this in a way that we're testing understanding and that we're fair to the two systems? Because it would be easy to write quizzes that made Raft look great. We just put really hard questions on the Paxos quiz. So what we decided to do was to use quizzes, but in a very structured way, where there are three different kinds of questions. First kind of question are just simple recall questions. If you watch the video and you go to the right place in the video, you can probably find the answer. The second kind is you have to take the video and apply it. So actually execute the algorithm. So you have to understand the algorithms well enough to execute them. And then the third and most interesting questions are, you have to extrapolate. So we give you a new situation, something not discussed in the lecture, but such that the information, if you understand Paxos or Raft, you have enough information, you could figure out the answer. And we had similar numbers of questions in each category and similar weightings in the exams. So we felt like this structured approach gave us a chance of having tests that were reasonably fair and equivalently tested the two systems. So then we ran the study. I have to tell you, I was really nervous before we did this, because neither Diego or I had any clue. We couldn't tell whether the results were going to favor Raft or Paxos. And we were wondering, what do we do if Paxos wins? Do we cancel the project at this point? Fortunately, the results were great, really significant results. Raft students did clearly better on the Raft test than the Paxos test. And in survey questions, students felt that it actually would be easier for them to implement Raft than Paxos, or to explain it to somebody else. My favorite statistic was that it turns out that students who learned Paxos first, some learned Paxos first, some Raft first. The students who learned Paxos first did significantly worse on the Raft quiz than those who learned Raft first. It's like a 25 percentage point difference, 6 points out of a 26-point average difference if you learned Paxos first. It's as if trying to learn Paxos makes it impossible for you to understand any consensus protocol, Paxos or anything else. Very, very surprising, amusing result. So then the question is, well, so did this make the program committees happy? We had these strong results from a user study. Well, no, they still weren't all that impressed by it. So a few were, there's more comments on the left side of the slide, but more people did not find it convincing. I think part of the problem was that we weren't able to explain the user study in enough detail to show all the things we did to try and make it fair. And so people might not be convinced about that. So unfortunately, that didn't really win over the program committees. It did, however, at least make it so program committees stopped complaining about the lack of evaluation. So at least we did eliminate that one complaint. Meantime, we were not getting much love from program committees, but boy, we were getting tons of interest from everybody else. We posted the paper on our website after the very first submission. And by the way, I strongly recommend doing this. There's nothing in the blind reviewing process that says you have to embargo your paper. You can release it publicly. Program committees are supposed to not look at it. And people started picking it up. In fact, Werner Vogels, the Amazon CTO, tweeted it in the spring of 2013. And then, boy, uptake started like crazy. We started getting emails. People started implementing it. Somebody suddenly formed a Raft Dev Google group. That actually wasn't us. It has hundreds of people on it now. And that's served as kind of a clearinghouse for people doing Raft implementations. Within a month of Werner Vogel's message, there were 10 implementations underway. There were 25 by the time of our NSDI submission. Program committee liked this fact, and they still rejected the paper. By the time the paper was finally published, it had actually been deployed in production. And by now, I think Raft is mostly displacing Paxos for production implementations. And the paper is now used in many graduate CS classes. So it's really clear that Raft hit a vein, and for exactly the reasons that we had thought originally. People would say, why are they using it? Because they can understand it and because the description is complete enough to actually implement from it. I have to say, projects that are succeeding like this have a particular feel to them. I've been fortunate enough to have a couple such projects over my career. And there's a really distinct feel to a project like this. I think the hallmark is that you start getting email from people you've never heard of about it. And that just happened with Raft. So there's a strange contrast between getting rejections from program committees and having all these people using them, clear uptake in the community. All right, so that's a brief description of the Raft history. Now I'd like to talk about some of my observations and what I think are interesting takeaways from all of this. And the first thing I'd like to talk about is problems with program committees. I think our program committees are problematic right now across the whole field. One of the problems, the biggest problem, is program committees are not able to predict the impact of the papers they're reading. They simply can't do that. I'm going to show you some data for that. So if you're willing to accept citation counts as a proxy for impact, I'll come back and talk about that in a second. Let's consider the Raft paper. So at the time I prepared this slide, Raft had almost 1,800 citations. I went through each of the 3 conferences that rejected Raft, and I took citation counts for every paper in all 3 of those conferences. And I've listed here the 3 top papers from each conference, along with the number of citations for those papers. Well, what's interesting is that Raft has 50% more citations than the highest cited paper of any paper in the conference. And it's not just Raft. So I went through the conferences, also looked up, there were best paper awards for those conferences. So this is the program committee's view of what are the highest impact papers. There were 6 award papers for those conferences. And I've listed those here along with their citation counts. And what's interesting is that of these 6, only one of them actually ended up in the top 3 of citation counts for the conference. And most of them are at the median or below. They're not even above the median. In fact, the program committees were barely better than a random pick. In fact, it's unclear they're any better than just random choice of best paper awards in terms of impact. So that's pretty shocking. Now, also you can ask, do citations actually measure impact? That's honestly, I have some concerns about that because citation counts tend to measure the popularity of an area as well as the impact of the paper. For example, one of the papers here, the scalable commutativity rule, I think is a really cool paper, great paper, but it's in an area that's just not going to generate a lot of citations. But overall, though, as I look at the papers with the high citation counts, in fact, these tend to be the papers that I think of as the highest impact. And 3 of these, for example, are papers that I've used repeatedly in my work and reference. So I think they are. I think citation count is not a bad metric of impact. But there's a bigger problem. I think that I believe that the whole mindset of program committees is wrong. I think the problem is that program committees come in with a negative mindset. They're looking for papers to reject. Figure we're only going to accept 10 or 20% of the papers. I've got to find a lot of papers to throw out. And this just produces really bad outcomes. It makes them conservative. So why take a chance on something that's bold or different? I'm going to have to reject a lot of papers. I'll just reject this one. They tend to focus on weaknesses. As soon as you find a weakness for a paper, reject it rather than focusing on the upside for a paper. And the result is they tend to prefer work that's not very controversial, small increment, so safe things, as opposed to risky things that are likely to be high impact. And furthermore, my experience in PC meetings is that negative always wins out over positive. If one program committee member really likes a paper, another one really doesn't like it, the paper gets rejected virtually every time. And actually, I found it's really hard to support a paper in the face of criticism when people start criticizing it, because after a while you start thinking, if I support this paper, then these people aren't just criticizing the paper, they're criticizing me personally. That I look stupid that I'm supporting this bad paper. And honestly, this is something I feel as a senior member of the community, I feel pretty secure about myself, but it's got to be a lot worse for someone who's junior, just getting started and doesn't have sort of personal security to stand up to the criticism. So you just cave. It's always easier to just cave and say, yeah, terrible paper, and pile on. So that's a problem. In fact, it's so bad that every program committee I have been involved with has had difficulty even filling the program. They're doing 15% acceptance rates and they can't find enough papers to fill the program. Literally, there are slots that are empty in the conference because they couldn't find enough papers to fill the program because the committee was so negative. It's just, it makes no sense at all. So I'd like to make an argument. Many of you are going to be on program committees in the future. Please, please, please have a positive mindset. Go in, look for the papers that you should accept, not the ones to reject. There aren't going to be very many that have really interesting ideas. Find those papers and promote them. Look for a paper with a bold new idea, even if it's risky. Look for papers that will stimulate discussion. Actually, papers that even eventually turn out to be a bad idea, if they generate a lot of discussion and thought, those can be really useful papers. Things that, maybe they have flaws or there's risk, but if they survive the risk, they can be high impact. So in general, I think enthusiasm should outweigh concerns about a paper. Much more important to have a paper that a few PC members really like than have a paper that nobody hates. It's much more important. And why not take a few chances? PCs don't like to do this. They don't want to take any chances, literally. People are worried, oh, we've got standards to uphold. We can't take standard chance. I hate that word, upholding standards. If you're going to accept 30 or 40 or 50 papers, why not accept 3 or 4 that are high chancey, risky? Give it a try. Those might be the papers that turn out to be the highest impact papers. And as you're reading papers, ask yourself, did I enjoy reading this paper? That's a really strong signal to me. Even if you think somehow, I don't see a contribution, but I really enjoyed reading the paper. That's your gut talking. It's probably an interesting paper. For example, in the NSCI 13 rejection letter, there was a summary of the PC meeting. They said, well-written and thought-provoking paper that reviewers enjoyed reading. However, the PCs struggled to identify the contribution. I think, wait, well-written, thought-provoking, people enjoyed reading it. That should be a contribution. Why not? But somehow the PC, they just sort of overthought it, the negatives went out, and the paper got rejected. So please, in your PC meetings, focus on the positive. Stand up for papers you believe in. Don't let yourself get talked out of it because one other person is negative on the paper. And one other comment on program committees. So my experience is that in the end, papers get what they deserve. The good papers find a way to be widely used. The bad papers sink into obscurity. I think we have this obsession, I think, in our field with the so-called top conferences, and everybody counts papers in top conferences. But honestly, papers in these lesser conferences can be just as successful. You know, the Raft paper is an example. Usenix is not considered as prestigious a conference as the ones that rejected it. And another example is the paper for which I received the High Impact Paper Award here on co-scheduling. I initially submitted that to SOSP, it was rejected. I published it in ICDCS in the early 80s. At that time, ICDCS was not a very well-known conference. I sort of assumed that because ICDCS wasn't very well known, the paper would probably never see the light of day. But in fact, no, people discovered it. It became widely referenced. Honestly, my view is that the quality of the paper matters a lot more than the conference. The good papers will rise to the top. And so I generally prefer not to spend a lot of time submitting papers to top conferences and having to get rejected over and over again. Do it once, get all the great feedback from the reviewers, and then find a place to publish the paper, and it will do what it will do. You'll end up in the same place. All right, some other observations. How to have impact. So I've been fortunate in my career to have had a couple of projects that have ended up having fairly high impact. And there's a theme among all of them. Each of these projects was based on a problem, either a problem that I had experienced personally, that's true for Raft or Tickle and TK, or problems that people near me were experiencing in VLSI design tools in the early 1980s. These ended up being very successful. Now, I've done other projects where we didn't have a clear problem we were solving. So for example, the RAM Cloud project was based on technology. We've got these fast networks and data centers. What can we do with it? Let's see if we can build a super fast storage system. Turns out, in general, these projects have had less impact. They've been less successful. There's a saying in the venture capital community in Silicon Valley, painkillers sell, vitamins don't. And that's kind of played out in my research, that if you want to have impact, find a problem that you're really intimately aware with, comfortable with. However, I do have to say, even though the RAM Cloud project itself hasn't had as high impact as other things I've done, in the process of building RAM Cloud, we discovered all sorts of other problems, like the need for a consensus algorithm that led to other work that has been more interesting. You know, we probably wouldn't have done Raft if we hadn't done RAM Cloud first. Now, the question is, well, how do you identify problems? How do you become aware of them? I'll tell you another favorite comment I've heard from venture capitalists. You have to put yourself in harm's way. That is, you need to be engaged at a really detailed level where you're going to experience the issues for yourself. So for example, me insisting that I need to understand Paxos before Diego implements it. I think many faculty tend to become managers rather than actual researchers. They leave all the details to their graduate students. Well, the problem with this is that you're not in harm's way. You're depending on your graduate students in order to see the problems. And you know, graduate students may do that, but you as a professor have a lot more experience and are much more likely to see them. I think it's really important to stay involved at a very detailed level, which is one of the things I've done in my career. I love to code. I still code. I always have coding projects going on, and I learn a lot from them. Another issue, so knowing versus proving. Now, I mentioned this survey I did of the NSDI 2012 attendees. I do that a lot. I just take small surveys of people. And I found that these surveys often expose truths to me. Now, they're not statistically compelling. You couldn't make an argument based on it, but the truth is there. And that doing these little surveys often tells you something important. Another example of doing this is before we started the Sprite distributed operating system project in the late 1980s, I went around to people at SOSP and I said, do you think there's really room for another operating system in today's world? And people pretty much all said no. Well, I really wanted to do Sprite, so we did it anyway. And sure enough, there was no room for another project. So, you know, it works both ways. Sometimes I listen to the surveys, sometimes I don't, but the surveys are usually right. So I find these really useful. Now, I have to say, when I did a dry run of this talk, many people objected to this. They said there's lots of places where these small surveys can be grossly misleading. You know, you need to be careful. And that's true. There certainly are counterexamples, but I found in many situations you can use them pretty effectively. Another issue, how do you deal with negativity? What do you do when you put an idea forward and a lot of people are saying, no, I don't think that's very good. So my advice is, if you really believe in the idea, don't give up. Don't, because oftentimes it takes a while for ideas to find their success and to get through to people. But the flip side is, don't be blind. Don't pursue it blindly. Pursue it with spirit and belief, but not blindness. And that means listen to the criticism and think about what people are saying and ask yourself, do I have responses to that? And so if you feel like you actually can work through the criticisms, then you should stick with it, because sometimes ideas take a while to propagate. So as Raft as an example, I had confidence in this from the very beginning, just based on my own confusion. I think that I'm probably not the dumbest person in operating systems. So if I'm confused, there's probably lots of other people that are confused also. And then I did this survey of NSDI, and of course, other people were confused as well. So I actually told Diego at the beginning of the project, I said, I think if we do this right, it's possible that Raft could displace Paxos within 10 years. And then indeed, there were these other factors that came in about, even though we were getting rejected, we were getting positive reviews and all of the uptake. And I knew there were skeptics. We read the negative reviews, but we felt like those skeptics were not typical of the community. They were the outliers. They were sort of the few people who really did understand Paxos. And I have to say, there's a certain deep fun that occurs when you have a project that gets a lot of disbelief in the beginning and then ends up being successful in spite of that. It's actually really rewarding when you eventually get the success. And I've seen this happen in enough projects now that I kind of enjoy it. Actually, even when Raft was getting all the dislike from program committees, actually, I sort of enjoyed watching that, because I felt pretty sure that it was going to succeed anyway, because I've seen this happen before in other projects. Now, I'm sure that all the rejections were pretty hard on Diego. Diego's really strong, but it's got to be tough taking all those rejections. But it has been fun in the end to see the project succeed. And then lastly, I'd like to talk a little bit about formalism versus intuition. So I've had a few discussions with Leslie Lamport in the years since Raft was published, and we have really, really different viewpoints. In fact, our viewpoints are so different that it's difficult for us to even have a discussion. But we've tried on a couple of occasions. And I'd like to try and do my best to present his view and my view. I think there's important distinctions there. So Leslie takes the view, a very formal view, that his view is that what's important about software are its mathematical properties. That's what's important. And he contrasts this with what he calls operational thinking, which I think that's the way I tend to think. Operational thinking is thinking about the behaviors, how it reacts in various situations and does things, as opposed to fundamental properties. And Leslie argues those properties are what's important. That's what you have to analyze in order to avoid errors. If you think operationally, you're going to miss lots of errors. At one point, I mentioned to Leslie my unhappiness when I had read the proof of Paxos, and I understood the proof, but I still couldn't understand why Paxos worked. I told him that really bothered me. That somehow, how could it make sense that I could understand the proof, but I couldn't actually understand the algorithm? And that didn't bother Leslie at all. He didn't see that as a problem. And he said, what do you need this understanding for? Isn't that just like a warm, fuzzy feeling? There's no real value to that, because people can think they understand something that's wrong, right? It's understanding, thinking you understand doesn't make something right. So he didn't think that was particularly important. And he said that simplicity, I'll get for simplicity. Well, simplicity is the simplicity of the mathematical description of something, sort of the conciseness of the description. And so by his definition, Paxos was incredibly simple because the mathematical description was very concise. And then his definition of abstraction, an abstraction is a formal specification for something. So that's Leslie's view. Now, my view is that first, I definitely see value in formalism. So I don't deny that. However, I think in most situations for most programmers, it's still very hard to apply formalism in a practical way in real programming. And just one example was Diego spent a huge amount of time on the correctness proof of Raft. It was really challenging. And he didn't really 100% finish. He got pieces, most big pieces, but he did not actually prove every single aspect of the algorithm. And in contrast, I think what's really, really important is intuition. This sort of gut level feel for, you understand how it works, and these basic principles of rules you can use to think about a system. And the reason for this is because you need to be able to, systems are living, breathing entities that are changing. You need to be able to work with them and make changes. And intuition is what allows you to do that in a way where the changes actually work. I actually think intuition is also useful in math, by the way. I'm doing proofs. Why does this proof work, for example? And for me, I have a different view of abstraction. To me, abstraction is a simplified view of a complex entity which hides unimportant details. The purpose of abstraction is to find a simple way of dealing with complex things. We try and design interfaces where many of the implementation details are not important, and so people can think about something with this. And furthermore, I really believe system behavior should be obvious. And what does that mean? That means if somebody just walks up to a system and makes their first guess about what's going to happen, that'll be correct. That's when a system's obvious. Now, Leslie would probably be horrified because he'd say, "What, you're guessing? How could you guess? That's crazy." But to me, we should try and design systems that are so simple that you actually can just make your first guesses so they work. So I think in general, intuition is undervalued in our field. Now, I will say, when I gave this talk as a dry run, a bunch of people spoke up and said, well, not all mathematicians have Lamport philosophy. And in fact, there's sort of this dichotomy in math. There are people that are more formalist, and there are people that are very intuitive in mathematics as well. So I think maybe Leslie is one end of the spectrum and I'm the other end of the spectrum, and there's a lot of space in between. But I really believe that intuition is really important. So just to summarize with a few conclusions. First, is Raft simple? Well, probably not. No, not totally simple. And I think the problem is that consensus is inherently complex. There are these two phases. That is fundamental. There must be two phases, each of which depends on the other in consensus. So one phase to get authority to do something and one phase to actually do the thing. But I do think that Raft is quite a bit easier to understand and work with than Paxos. I stand by that, and I think the evidence generally supports that. But a couple of other things, I think I take away, I hope you'll take, program committees are too negative. It would be great if we could somehow find a way of instilling a more positive culture in our whole reviewing process. And then finally, Raft has just really reinforced my belief in the power of intuition. It was so much fun trying to design something that would be easy to understand. Now, there's a lot of problems. How do you achieve it? I have some ideas, but I can't give you a recipe for it. How to measure it? Unfortunately, measuring is still very hard. We did the user study for Raft, but that's too much work for people to do in most cases. So it's probably not practical. And sadly, as a society, we tend to, if we can't measure something, we tend to devalue it. And so it's going to be a tough battle on intuition because it is hard to measure it. But I really believe in the value and the importance of intuition. I hope maybe I've infected a little bit of you, some of you, with that belief also. And then finally, why did we name it Raft? Well, there are three reasons for the Raft name. First one is that it stands for replicated and fault tolerant. The second reason is that a raft is something that you can build out of a collection of logs. And the third reason is that a raft is something you can use to get away from the island of Paxos. And so with that, I will stop and take your questions. Thanks for your attention.
Okay, thank you, John. This is a really wonderful presentation. To me, this is important message sent to the community and junior researchers. Delma and Abhishek, I have a question for you. How we ask questions, how audience ask questions?
So they can ask in UVA in the application. That's the way.
The question and answer.
That's.
Okay, I think there's chat. There are questions in, okay.
Shall I take the first question from the
yeah, please.
website, which says, shoot, it just reordered. I'll take the one that's the top right now, which says, John, great talk. What things should we change in our peer review process to make it better? Do you think it's at a breaking point that CS conferences will not remain that important in the future? So I think CS conferences will still remain important, sure. What do we do to make it better? Again, I think it's, well, first of all, we should recognize the weaknesses of the reviewing system, that it is really hard to measure impact. But I think, again, trying to instill a more positive approach, a culture. By the way, one of the problems is we have no institutional memory. You know, each program committee meets and then a new committee meets with a new set of chairs, and any lessons learned from the last program committee tend to be lost. And so somehow probably need to create some sort of institutional memory of how do we create a culture in our program committees about how they behave? Because we don't really have any, we don't have any rules like that right now. The second half of the question was, what are some important problems that the community is not paying enough attention to in the face of ML and AI wave? What will be the implication of missing those problems? So that one, actually, I don't have a great answer to. Important problems that we're not paying. I have my own sort of personal things where I happen to be interested in very low latency systems and data centers, but I don't think I have enough to give you a really meaningful answer to that one. So I think I'm going to pass on that question. Shall I go to the next one down?
Okay,
Sheldon, do you want to ask the questions, or do you want me to go? How would you like to handle this?
I think on the chat there's also a question, and then one question. Let me read this question. Great
Yeah,
talk.
I'll let you read the questions then.
Okay, during a great talk. I'm on the chat now. Great talk. During the design of Raft, what methodology did you use to test it actually works? It is really easy to miss corner cases when it comes to consensus.
Yep. Yeah. So we tend to use a methodology that's heavy on unit tests. And so unit tests are really good for testing things at a microscopic level and for catching errors of omission, of commission, where you do something wrong. They're not so good at testing errors of omission where you forget to do something because you don't write unit tests for that. And so it is easy to miss corner cases. And actually, we did miss one corner case. In fact, it wasn't until the third submission that we actually got the algorithm completely correct. In fact, David Maziere found the last problem. If you want to debug a distributed system, give it to David. He's probably the world's best distributed system debugger. There was one final corner case, which is, I think, the last figure in the paper, like figure 7 or figure 8, about where you have to only consider an entry committed if it's been committed in the current term. So we did miss that one, and that was just discovered fortuitously. By the way, it was not discovered by our attempts to prove it. We'd run model checking, and Dega was halfway, most of the way through the proof. Those did not discover the test. It was David Maziere reading the paper and saying, "I think there's a corner case here." It's not a very scientific way to do that.
Okay, next question. When simplicity should be given importance for real systems, why reviewers doesn't seem to like this simplicity?
Boy, that's a really interesting question. Reviewers don't seem to like simplicity. In fact, I've noticed, honestly, my impression is that a paper is more likely to get accepted if we explain it in a confusing way than if we explain it in a really simple way, because we explain it in a simple way, the program committee thinks there's nothing there. And they often downplay it. I found this, it just seems like papers that we have with more complex explanations are more likely to get accepted. By the way, that's another problem with program committees. So when you say, when should simplicity be given importance? I would say all the time. It's the number one thing I think about when designing systems. What limits our systems? What limits our systems is complexity, that they become so large and complicated that we simply can't continue to evolve and maintain them efficiently. The whole process slows down because of the weight of complexity. The only solution to that is simplicity. By making systems simpler, you can put off the accumulation of complexity. Can't stop it. It's a losing battle in the long run, but you can reduce the accumulation, which allows the system to become larger and more functional before the complexity catches up with you. So to me, simplicity is the number one single most important thing in system design.
Okay, there's another critical question. Why our professors have become managers and they are not involved in research themselves?
Well, I don't know if I can answer that question. It seems to be a fact. I don't know. Maybe maybe what happens is people that really like to code sooner or later go out into industry, which by the way, I did for a while. I wanted to build real software, but I found I loved academia. I loved teaching and working with students. So I came back to academia after 15 years in industry. I don't know why that is true, but I think it is largely true. There are very few professors who are deeply involved in coding. And I think if you don't do that, you lose your effectiveness. At some point, you're trusting your graduate students to discover and do all the important things, but you as a professor have much more experience and are in a much better position to discover the things that you will see if you're more deeply involved.
Okay, there's another one, a technical one. The fact that a long variant of Paxos, I think it's moving, Paxos was not clearly written down before is worrisome when I think of the distributed system community. Frankly, the canonical description for me is your YouTube lecture. Is the issue of field is young or too small in relative terms? Lack of good textbook. I think it's moving. There's a lot of questions. It's moving. In relative terms, lack of a good textbook and not incentive to democratize information that is inside large companies. Something else?
Yeah, so why wasn't this written down? It is very strange, that people were using it, that people had published papers like the Google Chubby paper describing an implementation, and yet somehow no agreement on this core aspect. So why is that? I mean, honestly, I think the blame for that has to go back to Leslie, that it wasn't in his interest. So again, Leslie was interested in the mathematical properties and in particular the safety properties. And so he focused on those, and those are important. I don't want to downplay those. But he didn't care about this, again, this operational thinking part about how it actually works. He figured those were details that anybody else could fill in. But the thing is, they're not that easy to fill in, turns out. And so the result is people did them in different ways, and we ended up with all this confusion. And then once there were several proposals, it was very difficult for any one proposal to come to the top. And that, by the way, that was one of the criticisms of the Raft paper. They said, this is just yet another Paxos implementation. We've already seen many people that have tried to do this. Why should we bother with this one? It's just yet another one. So it's sort of ironic that the more of them there are out there, the harder it is for anyone to rise to the top and solve the problem. And so I think eventually what Raft managed to succeed in that and get acceptance in the community. But it is very strange that we went this literally 10 or 15 year period where there was no clear consensus on how to build this thing.
Okay, next question. And first one is a comment. Maybe professors has a lot of funding related pressures. Great talk, John. Thanks. The next question is the questions are posted on here. Hi, John. Thanks so much for this great keynote. I'm among those teaching Raft in class. Here's my question. I'm wondering, what is the view on general complexity in computer systems? It seems that next to complex or distributed algorithms such as the Paxos, the combination of large number of simple mechanisms and interacting systems also causes a large complexity. How should we address this?
Yes, I agree with the problem. Complexity can happen at many levels. In Paxos, complexity happened at a very simple level. Just one very small thing was complicated, but in fact, actually more often complexity happens as the questioning person has said, that we have large numbers of mechanisms that all come together and interact in ways that cause complexity. So I don't have a trite answer for this. Actually, the best thing I can suggest, maybe a little too self-serving, is to read my book, where I've tried to talk about how to decompose systems in a way that we don't get too much complexity from the interactions. But it's a very difficult problem, very hard problem.
So, John, do we have any questions on your side on Hoover?
Let's see. I noticed you just read one from Hoover. Let me see if there's any other things. I'll read one. Thank you for the fascinating talk, really insightful. I have a question from teaching perspective. While many graduate CS classes teach Raft, there are some places that teach Raft in undergraduate classes. Do you have any comments or suggestions on teaching undergraduate students Raft? Presumably undergrad students might be less well prepared. I actually think, consensus is a pretty self-contained problem. It doesn't require a lot of other stuff to understand how to do it. So I think undergraduates can do it. Actually, I teach an undergraduate class called Software Design Studio, where the goal is to actually teach people software design and managing complexity. And the first project we do for that class, actually the first two projects are Raft, where in the first project, people implement leader election, and the second project, they implement log replication. Students really love that. They really enjoy Raft, and they enjoy implementing it. So I actually think Raft is totally suitable for teaching at the undergraduate level. Now, if you're actually going to implement it, it's a pretty significant implementation project. It takes most of the quarter for the students to do a complete implementation project for it, but it's lots of fun.
Okay, Dilma and Abhishek, do you have questions before I ask questions?
No, we're being respectful. I have many, but being respectful of the time, I think I'll just let you do it.
Okay. Okay.
I agree.
Abhishek?
I did have a short question, maybe kind of follow up to the discussion we had about the program committees. Do you see the fact that we have many more conferences as sort of a contributing factor to the negativity, like going more towards a journal model? Would that sort of help with some of these issues, do you think? Or are there other solutions that you see out there?
I don't think having more conferences is a problem. In fact, it's a solution to a problem, which is that because the field has grown and we have so many people doing research, we have to provide venues from the publish. We can't just keep shrinking the number of papers that get published. It's already, I think, very stressful for graduate students today. Certainly, I know my graduates, even it's, places like Stanford, you think of as a pretty good university, very high rejection rate still. And it's very hard on students. Boy, Diego is a really strong guy, but that's got to have been tough to get 3 rejections from top conferences in a row. It really causes you to doubt your self-worth. And the problem is we don't have enough publication slots. So I think if anything, we need to publish more papers. I've been arguing that I think more conferences need to go to multi-track. There's a lot of resistance at the so-called top conferences to that. I think we need to get by that. So I think the solution, if anything, is we got to have more conference, more slots, so program committees don't have to reject as many papers.
Thank you.
Okay, John, I'd like to take a privilege to chair the session to ask the last question.
Sure.
I have a philosophy of software design book in my bookshelf. My question is about teaching. In our system design, we always teach the basic concept of layers of abstractions. I think in this book, your book, you emphasize the decomposition of the problem decomposition. I can relate to problem decomposition, each layer of abstractions. Do you have any comments across the layers of decomposition, problem decomposition? I don't see this in the textbook.
Say that again. You're asking about
The problem decomposition
crosses software layers.
Yeah, do you have any comments about this? Because we are isolated to each other. For example, application people, they don't need to understand OS and architecture. They just write a Java program. So they don't know our problems. We probably also do not know their problems. So I can understand the problem decomposition in each layer of abstractions. So I'm thinking about any issues about the problem decomposition across the layers.
Well, my first thought is that if you've been able to divide the system successfully into layers where each layer doesn't need to know about the ones above it or below it, that's a good thing. And that we'd rather people don't have to have information that crosses layer boundaries. Right? That sort of increases the cognitive load that people have to deal with.
And also improve the productivity.
Right.
Division of the labors. That's also economic principle.
Yeah. And I would also say, when I I ask this question when I give talks on software design. I say, what's the most important concept in all of computer science? And to me, the answer is problem decomposition. That's sort of the thing that threads all of our fields. Well, when I asked Don Knuth that question, he said layers of abstraction. So you could argue if Don Knuth says that, that must be the right answer. But I slightly disagree in that I think layers of abstraction are one form of decomposition, but you can decompose within a layer as well. And so you can have interesting decompositions that are not necessarily layered on top of each other.
Okay, thank you. I think this is the last question. We've already extended this session to 10 more minutes. John, thank you very much. And also thank you all the audience to attend this keynote. And Dilma and Abhishek, you want to say something and then we end the session before we end the session. Okay, Songqing.
Something, yeah, maybe.
Yeah, thank you, Professor John Ousterhout. Very interesting, very fascinating talk. We appreciate you can joining us. And we very informative talk, and we learned a lot. And I think like ICDCS is also going to give best papers, and then best paper committee now has more pressure now. Thank you, everyone. Thanks for joining us this morning. I hope to see you in the evening demo and then tomorrow sessions as well. Thank you again.
Yeah, thank you, John, again.
Thank you for the invitation.
Okay.
I enjoyed this.
Yeah, bye-bye.
Great talk.